Okay, so mainly we're going to focus on linear approximations, which is section 3.8. But there is, back in 3.7, another derivative formula for a function that we haven't talked about yet. There's 6 trig functions, right? Sine, cosine, tangent, cosecant, secant, cotangent. And all of those 6 have an inverse function associated with it. And so in theory, we could talk about the derivatives of all 6 of our inverse trig functions, but it turns out the one that we're going to be mostly interested in is just inverse tangent of x. So what is inverse tangent of x? If I had a function y equals inverse tan of x, what this is basic, whenever I see something like this, here's what I think in my head. Okay, y is going to be an angle because we're doing it backwards. So y is the angle whose tangent is x. That's what you want to think of when you think of an inverse tangent. Okay, so you could even draw a picture here. You could say, okay, well, there must be some right triangle. Y is the angle. So y is this, usually we call that theta. And if the tangent of this angle was x, we can always think of x, tangent is opposite over adjacent, but we could always think of x as x over 1, right? Opposite over adjacent. So this could be x, this would be 1 here. Right, so this picture would describe what y is talking about. Now, in terms of the derivative, we don't know the derivative of this formula yet, but there's another way we could describe this picture here, right? We could also say from this picture, the tangent of y is opposite over adjacent is x. And this, we do know how to take the derivative of both tangent and x. Since this is not solved explicitly for y, it's not y equals, it's tangent of y equals, we're going to be doing implicit differentiation. So what we would next do is take the derivative with respect to x of both sides. The derivative of tangent of y with respect to x would be secant squared of y. We always have to tag on dy dx. Pay respect to x. That's what we want the derivative with respect to. Also remember that y is representing some function of x. In fact, y represents literally the inverse tan of x, right? That's what it equals. So that's why we're multiplying by the derivative of the inside. And the derivative of x with respect to x is just 1. If I solve for dy dx, I get dy dx is equal to 1 over secant squared of y. And 2 things here. We want to try to get this back in terms of x. Remember that secant is the reciprocal of cosine. So just like secant is 1 over cosine, 1 over secant could be thought of as cosine. And so 1 over secant squared literally would be cosine squared of y. And we could then use this picture here to figure out what the cosine squared of y would be. We are going to need to find this missing side here because cosine would be adjacent over hypotenuse, but that's easy to do. Let's say I call this c. So 1 squared plus x squared should equal c squared. C itself would be the square root of 1 plus x squared. That's this side. So the cosine of y, I'm going to put this down here, the cosine of y would be adjacent over hypotenuse would be 1 over the square root of 1 plus x squared, which means cosine squared, if I square this, is just going to give me 1 over 1 plus x squared, or 1 over x squared plus 1. It doesn't matter what order you add. Okay. And that is our derivative. And you are responsible now for knowing that. I mean, we can see how we could derive it, but that's going to be a little bit of work to try to do that every single time. So let's summarize then. The derivative of inverse tan of x is 1 over, let's go with 1 over x squared plus 1. Okay. Oh yeah, one other thing. Inverse tan of x is also known as arctan of x. I'll just put this right here. This is also sometimes referred to as arctan of x. And if you've been following along, right, the last few topics, we've been learning all kinds of new derivative formulas for logs and exponential functions. Once we know a derivative formula for something with just x in it, what's the bigger thing is, what if it was the inverse tan of something bigger than x, something like what I've been calling u, something uglier? Well, we know it would be 1 over u squared plus 1. And in the spirit of the chain rule, we would always then multiply by the derivative of whatever that ugly stuff was. So 1 over u squared plus 1 times du, the derivative of u. So just a couple examples on this. So if I had, let's say f of x equals inverse tan of, even something like x cubed plus 4, and I wanted to take the derivative of that, this would be my u. That's something more than just x. And so the derivative of inverse tan of stuff would be 1 over my stuff squared plus 1 times the derivative of just the stuff, not the whole thing squared, just the stuff. So this would just get multiplied by 3x squared. And if you wanted to simplify this, this is in the numerator, so you just multiply it straight across times the 1. You would get 3x squared over x cubed plus 4 squared plus 1 would be my derivative. Let's see, what else could we do? We could say, say I had y equals x times inverse tan of, let's say, e to the x. Okay, then we can have these just like always. This can be part of a product rule, right? This is x times another function. So here would be f. This whole thing would be g. Our derivative setup would be f prime g plus f g prime. The derivative of x is 1 times g tan inverse of e to the x plus f, let's slide that up, which is x. And the derivative of inverse tan of stuff is 1 over my stuff squared plus 1 times the derivative of my stuff, which would just be e to the x. I'm going to leave it. Oh, this is y prime. There we go. I'm going to leave it like this. All right, so we'll add that to our list of derivative formulas to make sure we know. All right, moving on. So here's the real thing I wanted to talk about today, linear approximations. There's actually quite a bit of stuff in 3.8. There's linear approximations, there's Newton's method, there's the idea of error propagation. So we'll see. I'm just going to talk about regular linear approximations, and we'll see. I might make another video, or we can discuss later those other things that are in 3.8. All right, so as the name implies, what we want to do is approximate things. Linear means with a line, and in particular, what a linear approximation, kind of another name for this, would be a tangent line approximation. Tangent line approximation. So we're back to that idea of what is the derivative telling us about a function at any point. It's giving us the slope of the tangent line. And so we want to approximate the square root of 38 ultimately, which is something probably you couldn't do in your head, although you should know the square root of 38 is roughly 6 point something. And how do I know that? Is 38 is close to 36, and the square root of 36 is 6, exactly. So I know already my answer is 6 point something, but I'd like to get a better approximation for that. So here's the idea, okay? We ultimately want to approximate the square root of 38. So imagine like here's x equals 38 here. Straight down. And if I went horizontally from this point here, this y value would be the square root of 38, which is what I want to know. But that's my trouble, is I can't do that without a calculator. I can't get an accurate answer without a calculator. So this x equals 36, I'm using what the book does. They describe it that way, but they'll also refer to this as a equals 36. They'll use a in the formula. And the way to think of this is the, I like to call it a nice number close to where we want to approximate our square root function, which is at 38. And so I know 36 in reality is really close to 38, but I'm going to just stretch this out so we can really see what's going on here. So let's say 36 is right here. And this, of course, is an easy value, right? This is the square root of 36, which we know is 6. Can work that out. So the idea is going to be this. At our nice number, we could draw a tangent line to our graph right at 36 at our nice number. So here's our tangent. And the idea is going to be this, that instead of plugging in 38 into our square root function, which we don't know what that answer would be, when we find the equation of this tangent line, we're going to plug 38 into our tangent line. And it looks, for one thing, I can tell I'm going to be over, right? It's going to be an overestimate. And that is something that you may be asked to determine whether your tangent line approximation is going to be an overestimate or an underestimate. And it looks like quite a bit of an overestimate, but remember, I stretch these points out. In reality, 36 is pretty close. This is not a very big difference. And in fact, this distance right here, how far my tangent line is from my function, that would represent my error, how far off I'm going to be. Okay. So let's get to the formula here. So I'm going to give you the general formula first. And so if we label this point, I know I have 36, but in general, this point, we can call this a comma, whatever the value of the function is at a f of a. Just using your regular equation of a line, y minus y1 equals m times x minus x1. My a f of a would be my x1, y1. So I would have y minus f of a. What gives me the slope of my tangent line? Well, we know by definition that is the derivative, right? That would be the derivative at a. So the slope is given by f prime of a times x minus my x1 is a. And then all we do for the formula is I'm going to move this f of a over. So we have f of a. I'm not even going to distribute like we sometimes do when we're writing equations of tangent lines. You'll see why it's easier to leave this factored out. So this then should be just y on the left side, but to really emphasize that we're doing a linearization, we'll call y, instead of f of x, let's call it L of x, the linearization, okay? I'm just going to bubble this part because this is the formula you're going to use repeatedly in this section for your linear approximation, which again just is really just a general equation for a tangent line. All right, so let's put this into action here for our problem. Our a value was 36, so our linearization is going to be f of 36 plus f prime of 36 times x minus 36. Remember my function, I'll put it up here, was the square root of x. So it's easy to see f of 36 is just the square root of 36, which is 6. The derivative, though, we might have to work that out. The derivative of root x is 1/2 x to the negative 1/2, which, because I'm going to plug in a number, I'm going to simplify this. X to the negative 1/2, since it's to a negative power, can come down underneath in the denominator. And so I can think of this as 1/2. Once I bring it down, it's x to the 1/2, which is root x. So then I can see that f prime of 36 is going to be 1/2 square root of 36, which is 1/2 times 6, 1/12. Times x minus 36. So this is a form of equation of a line here, right? And so the next thing what we wanted to do was to plug in, we want to estimate the square root of 38. So we want to now plug in 38 for our x value. L of 38 is 6 plus 1/12, 38 minus 36, which is 6 plus 1/12 times 2, which is 6 and 1/6, 6 plus 1/6, 6 and 1/6. So what this tells us then is the square root of 38, I'll put therefore, the square root of 38 is approximately, it's a pretty good estimate, 6 and 1/6. And that's usually all you have to do, but occasionally I've seen professors ask, is this an overestimate or an underestimate? And again, that's where the picture comes in handy. I think you should be able to sketch out a picture of what's happening here to see that. We can tell that our tangent line is over our function at 38. So our answer of 6 and 1/6, which is for our tangent line approximation, this is 6 and 1/6, is actually an overestimate. Oh, can't see that. There we go. All right. Let's look at another one here. We're going to estimate 1.98 to the 4th power with a linear approximation. So what you see here is it gives you the ability to estimate things. I mean, I know you could all multiply 1.98 times itself 4 times without a calculator. It'd take a lot of work, a lot of effort. And so that's what these are really useful for, is approximating messy calculations with not too much work. So in the formula, which we saw, let's rewrite our formula. Our L of x is f of a plus f prime of a times x minus a. Basically, you have to just decide on a couple of things here. Number one, what function should we be using? Well, this is kind of common sense. If we're trying to estimate a number like 1.98 to the 4th, then we should probably be thinking about the function x to the 4th, right? Our x value is this messy number, 1.98. That's what we want to be plugging in there. And then remember, the idea of a is a nice number that's close to 1.98. I think obviously the number here would be 2, right? So we want to pick this number because it's close to 1.98. And so with that, you don't even need a graph. If you want to, for some problems, you can just go ahead and plug into the formula here. So L of x is going to be f of 2 plus f prime of 2 times x minus 2. F of 2 is just 2 to the 4th, which is 16. We do need the derivative. That's 4x cubed. So then if you plugged in 2 here, that's going to give you 8 times 4 is 32. sometimes, I don't know why they would just do this, but sometimes they just ask for the linearization. They just want this and you're done. But to me, the whole reason of a linearization is to be able to approximate something with it. So, but yeah, usually I do it in terms of X. And then if they give me a number, ultimately we want to know what L of 1.98 is. And that's going to be 16 plus 32 times negative 0.02. And that's 16. So the way I do my math in my head, 32 times 2 is 64. So if it was 32 times 0.2, it would be 6.4. And it's 32 times 0.02, it's going to be 0.64. And it'll be minus. So minus 0.64. And I get an approximation of about 15.36 is, so I could just go ahead and say that 1.98 to the fourth is approximately 15.36. If they asked if this is an overestimate or an underestimate, let's just talk about that one more time. Then you would want to think about the graph. So I'll put over or under estimate. You actually want to think about the graph and think about what just happened, what our tangent line looked like. So the graph you would be thinking about is f of x equals x to the fourth. Which is, some of you know, that's just like a steeper version of a parabola. So it would look something like this. The nice number we used was 2. That's our a value. Our a is 2. And our messy number was 1.98, which again is really, really close, but we're going to really see it. We're going to move it over a little bit. That was our x value. And remember that the tangent line is always drawn from the nice numbers. So what we would have seen, what we just worked out here was basically our L of x was really the equation of this line. This is our linearization. That's our linearization. And you can then see that what we really did was that 15.36 was plugging 1.9 into the tangent line, which we can see is under the actual value. The actual value would have been on the actual function. So from here, you can see this is a slight underestimate. Obviously, if they're going to ask you that, they got to ask you that for a reasonable graph to draw, something that you should know how to graph. So, and I'm not even sure, not every professor would ask that, but I think it is a good question. In fact, I tell students, if I was your professor, I would ask that because I want you to know what's happening. So just a couple more practice here. We won't worry so much about overestimate or underestimate. And so maybe, so if you're watching the video, you can pause it. You can pause it and try to estimate the natural log of 1.05. You'll have to decide on your function, your a value, and your x value. So if you want to give that a try, go ahead and pause the video. So our function, if we want to estimate the natural log of something, our function is going to be ln of x. Our x value is the messy number, and our a value is the number close to 1.05, which would obviously be 1. And that brings up an issue. What if it was like 1.5 or something, right in the middle? Well, you could either go with 1 or 2. One thing you see from, let me go back to this one, from what's happening graphically, like you want to have your nice number close to your messy value, because look what happens to the tangent line. It keeps going away from our function. So if I had tried to approximate back on problem number 1, like the square root of, I don't know, 45 or something like that, right? Then my my tangent line approximation is really far from the actual value. And you can see that my error gets a lot larger the further I am away from my nice value where I construct my tangent line. So what would you do then? Well, if I was using 45, if I wanted to approximate the square root of 45, I would not have used 36. What would have been a better choice for my nice number? I would have used 49, right? Because the square root of 49 is 7, and that's closer to 45 than 36 is. So usually it's a pretty obvious decision to make what your nice number is. So it's like 1.05 is definitely closer to 1. Okay, I know I'm going to need the derivative, so we'll just work that out. 1 over x. L of x is going to be f of a, so f of 1 plus f prime of 1 times x minus 1. F of 1 is the natural log of 1, which happens to be 0. F prime of 1, plug that in here. That's just 1. So my linearization formula, literally in this case, that's 0. It's 1 times x minus 1 is just x minus 1. And if I were to approximate 1.05 by plugging that in there, that just gives me 0.05. So what that tells me is the natural log of 1.05 is just approximately 0.05. And how about one with a trig value here? So what if I wanted to know the sine of pi? Sine of pi you should be able to do, but what if we did just a little bit more than pi? Remember, pi is 3.14 radians. So what if somebody asked you to do the sine of 3.14 plus 0.04, which is about the sine of 3.18 radians, right? That's roughly what this is saying. So again, more practice. If you want to pause the video, give it a try, see if you can approximate it, and hopefully you tried it. So now we will do it. So what's our function? If we're trying to estimate the sine of something, we're going to be using sine of x, which we might as well get the derivative. Our x value is going to be pi plus 0.04. And our a value, our nice number, well, it's just a little bit hair bigger than pi, so let's just use pi. So we're going to want f of a, so f of pi plus f prime of pi times x minus a, so x minus pi. I'll just go ahead and write this out. F of pi is sine of pi. F prime is cosine of pi, because that's the derivative. Sine of pi and cosine of pi, you should be able to get those here. I'm going to just draw I'm going to need both of those. I like to think of those from the graphs. If you want to use the unit circle, that's fine. But the graph of sine is pretty easy, and you should know what that graph looks like anyhow. Finishes off at 2 pi. So pi is right here. I can tell that the sine of pi is going to be 0. Cosine, really easy graph to construct, starts up at the top. Does one complete cycle at 2 pi. So pi would be right in the middle here. I can see that the cosine of pi is -1. So it's going to be 0. Cosine of pi is -1 times x minus pi. So that would be my linearization formula. And if I want to evaluate sine of pi plus 0.04, that's 0. It'd just be -1 times pi plus 0.04 minus pi. And that's just going to give me -0.04. So the sine of pi plus 0.04 is approximately -0.04. And perhaps you could see why it's going to be negative. from the graph of sine, right? If this is pi and I just asked you the sine of pi plus a little tiny bit, you can tell it's going to be something negative. All right, one last problem here, and this one's a little bit different, more in a context problem. Suppose the per capita growth rate of a population is 2. The population size at time t equals 5 is 100. And we want to use a linear approximation to estimate the population at time t equals 5.1. So this seems a little weird because they didn't give us a function, did they? Didn't give us a function, but in reality, they kind of did. They kind of at least gave us enough information to answer the question. Let's think about our formula here. L of x equals f of a plus f prime of a times x minus a. So there's some information. So first of all, we're going to be doing it in terms of t, right? And you can tell that one of the times is 5. We got a nice clean number here. We know the population size at 5 is 100. And so you could interpret this as saying whatever the function is for our population, we know that f of 5 is equal to 100, right? That's our, in other words, this is going to be our a value. 5 is our a value because it's a nice number. Now here is an unnice number, right? Not so nice. So this is going to be like our, well, our x value, but we'll probably switch this to t. This is going to be our t value. So we've got f of a, we've got our t value, we've got our a value. So the next thing we need is the derivative. And that comes from this first sentence here, because earlier in section 3.6, we talked about what we mean by a per capita growth rate. And in fact, I'm going to use n. If n is the population size, that's how we talked about it in 3.6, then dn dt is the population growth rate, if you recall. And if I take the population growth rate and divide by the actual population size, which was the same as multiplying by 1 over n dn dt, that's what we were calling the per capita growth rate. So what they basically have told us in this first sentence, if the per capita growth rate of our population is 2, what that tells us is 1 over n times dn dt is equal to 2. Now, how can I use that? For one thing, now I guess I'm kind of switching over here. If we're going to talk about a population, so let's use n here since I've introduced it here. So instead of f of 5 being 100, let's interpret that as n. The population at time 5 is 100. Okay, we're going to use n to represent our population size. What we need now here is the derivative at 5. Well, dn dt is the derivative. Remember, another name for that is n prime. And so if I multiply the n over, n prime of t is going to be just 2 times n. So if I wanted the f prime, I want n prime of 5. That's going to be 2 times the population at 5, not 2 times 5, but the population at 5, right? That's what n represents. So we know that the population at t equals 5 is 100. It's going to be 2 times 100, or 200. All right, let's rewrite. I started writing L of x, but let's rewrite it in the context of this problem. For our linearization, it's going to be n of t. We want to know the population at time t is going to be n of some nice number, namely 5, plus n prime of 5 times t minus 5, not, or t minus a. Okay, sorry. We'll just, I'm kind of generalizing and then plugging in at the same time. So n of t would be n of 5 plus n prime of 5 times t minus 5. The population at t equals 5 is 100. We just figured out that the population when t equals 5 is growing at a rate of 200. And for our t, well, let's just leave it as t minus 5 for now. And ultimately, we wanted to know, the problem asks us for the population at a messy time, which is 5.1. So we can plug that in. This is going to be 200 times 0.1. 1/10 of 200 is 20. So this is approximately 100 plus 20. Our population is roughly 120 at 5.1. Kind of a different type of a problem, but you see hopefully that you can still use that same linearization formula. You just have to extract the information from the problem. All right. Thanks for watching. Bye.